this video, I want to talk about the two conformers I have here of the cyclohexane, and this is one chloro and then one, two, three methyl cyclohexane conformers. Then we have the equitorial on the left and the axial on the right. I've labeled these A and B, but we can also just say this is the equitorial and this is the axial. And the reason it's axial is because these substituents are both pointing up. If you think about chlorine, it's a pretty large molecule, and the methyl group is fairly large too, considering the size of this molecule as a whole. I call chlorine a molecule; it's an atom. All right, but the chloral group and the methyl group are going to um, have some steric hindrance, which makes the axial conformer less stable. So the equatorial conformer is preferred. And if you look at the energies of these guys in kilojoules per mole Kelvin, or no, just kilojoules per mole, the one on the left, as calculated by a Spartan modeling program, is 212.707 kilojoules per mole, and that's the heat of formation, delta H naught. And the delta H naught, there should be a delta here, but I ran off the screen, so let's throw a delta. The delta H naught on the right one is it's equal to negative 199.435 kilojoules per mole. So if you remember, that's how much energy is released when these guys are formed. Forming bonds releases chemical energy. Alright, now which one is more stable? Okay, the one on the left is the more stable one. It's at a negative, it's more negative, and so more energy was released for this guy. Alright, and delta H not being negative means that it was like an endothermic process, or the energy was released. The negative sign tells us a lot about this reaction, about forming this stuff. But what I want to do in this video is just concentrate on how much, what is the percentage of each one of these guys in solution. So if we were just to make them, maybe these two conformers are both existing in solution, and one molecule is just going to switch really fast between each conformer. I've heard up to maybe like 1,000,000 times per second. You can look into that, but they switch like flip-flop between each conformer super fast. So the difference in energy is what we call delta G, and that's the Gibbs free energy. So the Gibbs free energy for these guys is, we'll look at we'll consider this to be some kind of equilibrium, which means that we have an equilibrium constant, which is the products over the reactants. And so we'll consider molecule A to be the reactant and B to be the product, even though this equilibrium it does exist, I guess, in solution, but we're not like forming something entirely new here. But let's just think about it and model it this way for a second. So B has an energy of minus 199.435 kilojoules per mole, and we subtract away the energy from the reactant. Sorry, 212.707 kilojoules per mole. Alright, so we just took our product's energy, delta H product minus delta H reactant. And so this gives us a delta G value of positive 13.272 kilojoules per mole. And hopefully in a general chemistry course you've learned that if delta G is positive, that means that this is not spontaneous. So what does that tell us about these two relative to one another? Well, if going from A to product B is not spontaneous, then A must be of greater stability than B, right? So take some time to think about that. If we look at B, that's as the product, then this is not spontaneous. But if we flipped it around and we looked at A as the product, then we would have had a negative 13 here. Alright, if B was the reactant and A was the product, and this reaction went the other way around, then it would have been a spontaneous, so to say, in the way that we're modeling this. So let me clear the screen and we'll do a calculation to see what percentage of each of these is. So I cleared the screen and we're going to do a calculation. If you remember from Gen Chem, delta G is equal to minus RT times the natural log of Q, where Q is the instantaneous equilibrium constant, dependent on the temperature. So let's consider the temperature to be 23, or just room temperature. So that's 23 degrees Celsius. This means that delta G, 13.272 kilojoules per mole, is equal to minus, and then this is our temperature gas constant. This is our gas constant, right? So if we're working in kilojoules per mole, that's 0.008314 kilojoules per mole Kelvin. Alright, and then the temperature is 23 plus 273.15. We have to add the 273.15 because we need a temperature in Kelvin, so that our units Kelvin are going to cancel, and that's times the natural log of Q. So solving for Q, I can just do this in one step. Q is equal to E raised to the negative, what we had on the left side, 13.272 kilojoules per mole, right? And then that's going to be divided by, so I'll just put 1 over 0.008314 kilojoules, and then we have mole up here, so you see our units are going to cancel, and also divided by the 1 over 23 plus 273.15 kelvins. Alright, and that canceled with the rate constants kelvins. So if we run that calculation, we get Q equals 0.00456, and what that tells us is that in equilibrium, well, at this temperature, right, at 23 degrees Celsius, we're going to have 0.00456 equaling to the ratio of B to A. Basically, we're going to have a lot more of A than we are of B. So how much more are we going to have? Well, the way I do this is, let's just think about the equitorial axial thing, right? So 0.00456 is equal to the ratio of the axial, right, to the equatorial, which implies that the axial product is equal to 0.00456 times the equatorial product, right? And we can write another equation. We can write 100 And if we think about percentages, well, percent equals, or percent is like how much out of 100. So we can say 100 is equal to the amount of the axial plus the amount of the equatorial. And what this means is that, well, we can just substitute axial here with all of this business. So we have 100 equals 0.00456 times equatorial plus equatorial. Alright, so let me just clear this stuff up top real quick. So I kept our equations here. Alright, but what we can think about is this is one equatorial right here plus 0.00456 equatorials, right? So what that means is that 100 is equal to 1.00456 times the amount of equatorials there are, and that's going to give us that the amount of equatorial is equal to 100 over 1.00456, right? And so using a calculator, I got that basically the percent of the equatorial is 99.546, right? And that also implies that the axial percentage is 1 minus that, or 100 minus that amount, and that's equal to 0.454%. Alright, so that's how you run that calculation. So we know that now at equilibrium, or just at room temperature, that the equatorial is much more favored than the axial. So we see a lot more of those. Alright, thanks.